Hello, so today for my Chem Winter Culminating project, I'm going to be discussing chemical equilibrium. So I'm going to begin with an overview of what we went over in the Module 8 lectures, and then I'm going to go more in depth with an example of how Le Chatelier's principle functions, and specifically the concentration effect of changing the concentrations of the products and the reactants. So up until now, we've mostly dealt with reactions that have always proceeded as the starting materials turning into the products, and this is depicted here by this normal arrow. But something that's very important is that they do not always go to completion, and this can be represented by the equilibrium arrow, which I have right next to it, so you can compare the two. This also means there is not always a limiting reagent. So chemical equilibrium is the state of reaction system where the forward reaction rate is equal to the reverse reaction rate between the two substances. And in this case, we have the starting materials and the products. And this is pretty much a description of why it is a dynamic state. And the concentrations of reactants and products remain constant at equilibrium. So I added an image to demonstrate that. So here we have A and B, which one would be the starting material, one would be the product. And they both begin, one begins with no concentration, one begins at 100, and then eventually they level out. And here where they're flattened out is that where they're at equilibrium. So to know equilibrium, you got to know the equilibrium constant, which is the K value. So since the amount of starting materials and products remain constant, there's an equilibrium constant also, which is expressed by K, and every equilibrium reaction contains a constant K value for when the reaction is at equilibrium. So it's usually at a certain temperature that exists. And it is determined by taking the concentrations of the starting materials and products at equilibrium and putting them into this equation. So for example, if you have a similar equation, this is just with letters, we'll go through a real example, but the letters in front would be how many moles you have, and then that would be the A and the B and the C and the D would be the product. So you'd rearrange it like this with the products on the numerator and the starting materials in the denominator to the power of whatever those number of moles are at the beginning of each one. And that's how you want to set it up for each equation. And as well, a reaction quotient exists depicted by a K, or a Q, my bad, K is the beginning one. And the reaction quotient can be determined by entering the concentrations of starting materials and products there at any point of the reaction into the same equation. So to do this type of reaction, you do not have to be at equilibrium. So it's depicted by the same setup here, but you do not have to be at equilibrium to just find the Q value. You can do this at any point in the reaction. And as well, there is a relationship between K and Q, and then I'm going to further discuss that in the next slide. So the relationship between K and Q is a bit simple in these terms. After calculating or determining these two values, there are assumptions that can be made. They are the following. So if Q and K are the same value, that means the reaction is at equilibrium. And it's usually depicted by the arrow that I've shown earlier, the 2A. But if the equilibrium constant is bigger than the quotient, then the reaction goes toward the products. And this can be depicted by a larger arrow going towards products. And this is done because you want to be at equilibrium and the reaction does want to be. So, and as well, if the quotient is bigger than the equilibrium constant, the reaction goes toward the reagent. So this is depicted here as the larger arrow going towards the reagents as well to reach equilibrium. So there are a few principles, but today we're just going to focus on the concentration effect. As well, I've added a photo of Henry Louis Le Chatelier, who discovered these principles here on the right. And the concentration effect states that increasing the concentration of starting materials or decreasing the concentration of products shifts the reaction toward the products. And this makes sense because we want to be at equilibrium and keep the two rates equal. And as well states by the opposite of increasing the concentration of products or decreasing the concentration of starting materials shifts the reaction toward the starting materials. And because we want to be at equilibrium again, and I'm going to go through this concentration effect by an example. So here we have an experiment. This would be known as experiment 1. The whole equation is at the top there. And so it's lead and chromium reaction, and they're in equilibrium with each other. I've retrieved this from the textbook, and just a quick reminder that this is the equilibrium constant for this reaction when it is at 25 degrees Celsius. So it can change by the temperature. And also keep in mind that lead solid cancels out because we do not take into consideration solid or liquid states into these equations. So in the initial, we only have starting materials present. Therefore, the quotient is 0, which I have 0 here in the equation because 0 is the products and then the starting materials on the bottom. And then to find K, I've plugged in the same amount of stuff. And in the textbook, it gives us the equilibrium constant to be 3.2 times 10 to the negative 10. And we're going to explore what happens when we change all of these values to the initial values and the equilibrium values and how that changes Q and K. So for this reaction in particular, Q is larger than K. So if you guys learned from last slide, the reaction will shift towards the reagents. So here we have experiment 2. So we have a lot of starting material in the initial and very few in the products, as you can see. This is a bit different from what we've had before. So plugging this into the equation, reaction quotient here, we come up with a quotient of 3.2 times 10 to the negative 10. And in the equilibrium, we're increasing the amount of products. As you can see, they went up a bit. They're still in the low numbers, but they did increase. And we're decreasing the amount of starting materials, as you can see here as well. So K stays the same because the equilibrium constant remains the same, remember that. But as you can see, since the K value and the Q value are the same, that means that the reaction would be at equilibrium in this case when you're identifying what's happening at the Q value. And now we're going to explore one last experiment. So this would be increasing the reactant concentration. So here we've decreased actually the products even more than to begin with. And also for the initial, we have more starting material and fewer products as well, which is kind of the basics. And we've decreased the amount of products in this example. So the quotient was determined here, and it actually became a lower number than all the others. It's actually 2.5 times 10 to negative 12 in this case. And the K value comes to be the same answer as well with all these different values, as well as 3.2 times 10 to the negative 10. And since in this case, Q is larger, Q is smaller than K, the reaction will shift toward the products. So we've seen 3 different cases, all with the same equation, and how Q and K relate and how the concentrations can change, but the equilibrium constant always remains the same. So that's the main part, what I want you guys to kind of see in this, and how equilibrium shifts in their concentrations to show this. And here are my references. Hope you guys learned something today.